toy rocket moves in the y direction with an acceleration given by the equation a equals 50 minus 2t squared, where t is time in seconds and a is in meters per second squared. At t equals 0, the toy rocket is located at position y equals 10 meters and has a velocity v equals 6 meters per second. Which of the following correctly represents the position y in meters of the toy rocket as a function of t? Okay. So it's important to start off by writing out what we have for acceleration as a function of time, which is just 50 minus 2t squared. Now, the function of velocity with respect to time is just going to be equal to the integral from 0 to t of a of t with respect to t plus the velocity at time t equals 0, so plus v of 0. Now, let's substitute in 50 minus 2t squared for a of t. So that'll just be the integral from 0 to t of 50 minus 2t squared with respect to t. And v of 0 is given to be 6 meters per second. But we don't have to write out the units since we're writing this as a function. And so v of t is going to be equal to negative 2t thirds plus 50t. So all I did was just solve that integral and plus 6. And then we're going to do the same thing for y of t. It'll just be the integral from 0 to t of velocity with respect to time plus y of 0. And if you're curious, the reason why the lower bound of the integral doesn't show after we integrate is because 0 times anything is 0, and so when we substitute that in, we just get 0, and minus 0 is going to be the same. So y of t equals integral from 0 to t of velocity, and so negative 2t cubed thirds, integral of that will be negative t to the 4th sixths, and then plus 25t squared plus 6t plus 10. And so that's our equation for y of t as a function of time, and that corresponds to answer C. In the time interval from t equals 0 to t equals 5 seconds, which choice correctly describes how the position and velocity are changing? So let's start by rewriting our equations for acceleration and velocity as a function of time. This is because if we want to determine if the position and velocity are increasing, we need to analyze the behavior of the derivatives, and the derivative of position with respect to time is velocity, the derivative with velocity with respect to time is acceleration. So if we're going to see if they're increasing or decreasing, we must see if the derivatives are positive or negative. So let's just draw this numbered line to help us out. So we'll write the bounds from 0 to 5 seconds, and we'll label them with v and a. And now, it's easiest to start with acceleration because it's the simplest equation. So we're just looking for the critical points, or when this is equal to 0. So a of t is going to be equal to 0, so 50 minus 2t squared equals 0. So add 2t squared to both sides, divide both sides by 2, and then take the square root of both sides. And the reason it's not plus or minus 5 seconds is because you can't really have negative 5 seconds. And so acceleration is going to be positive from 0 to 5, exclusive of 5, and 0 at 5 seconds. So now let's write v of t equals negative 2t cubed thirds plus 50t plus 6. And now we're just going to solve for when this is equal to 0. But first, I want you to notice that if we factor out the t from the first two terms, we get v of t equals negative 2t squared thirds plus 50 times t. And so notice that negative 2t squared thirds is always going to be less than negative 2t squared, or at least the magnitude will be less than it, and therefore it will take more time for it to be equal in magnitude to 50, and velocity will be positive for that interval. And that's also neglecting the term of 6 outside, so it'll take you more time than that. And so because the velocity and acceleration are positive on these intervals, and yes, I see that acceleration is 0 at 5 seconds, but it doesn't matter because it's increasing for every other time t before then. So because that, the velocity and position are increasing on this interval.